Hello everyone, welcome to Chapter 5. We will deal with integration, the second part of calculus. The first part we did derivatives. Here we do integration or finding integrals. And we begin with focus on area and estimating with the finite sums. Let's say for popular shapes, and you can think of a rectangle, a square, a triangle, you can even think of 3D figures, right? A cube or anything, a prism, circle, oval. So all these popular shapes, we can find area, right? We can find the area using geometry. And geometry has given us a number of formulas to help us find the area, the volume, the surface area, and so on. And so if you're really focusing on area, which is a two-dimensional information, we've got that in geometry. So the question of finding area in calculus comes in when you're talking about not popular shapes or familiar shapes, but about area under a curve. And that curve can be any curve, right? It could go anyhow, it could be irregular. And so that is where calculus comes in. So I'll just say, to find the area under the curve, under a curve, we use, it is done through calculus. To illustrate this, let me begin with a simple equation here, which is a polynomial of degree 2. Take a look at this graph. 1 minus x squared is a polynomial of degree 2. It's a quadratic equation, a function that will give you a parabola. And here, the focus is only in this blue shaded region. So we are asked to find the area for this blue shaded region, even though we know that this equation would extend the graph indefinitely on both ends. The focus is only for this defined region. So to define this region, actually, we can use, if we were to define this in words, then we will say find the area of the shaded region and they've called that region capital R, so we'll say R, that lies above the x-axis that is true, below the graph of y equals 1 minus x squared, so below, under the curve, yes, and between the vertical lines x equals 0 and x equals 1. So we're kind of covering it on all four sides to define this region, right? If I didn't give you the graph and if I just gave you this description, if you followed the description, you would end up with this graph, right? Because x equals 0 is nothing but your y-axis. Or you can see it as a vertical line as indicated here, which is x equals 0, and then you have another vertical line, x equals 1, so there will be a vertical line here. And this is the graph, so we're looking at the area or the region below the graph. So it's below the graph, above the x-axis, and bounded on the left and the right by the vertical lines x equals 0 and x equals 1. This is the kind of language you'll begin to see in this area problems. Okay? Anyway, so how do we find the area is the question. Clearly, you can't use geometry or use any specific formula. We do not have that. So we have to then rely on this technique of estimation using geometry. Okay? Because geometry is established, we know that. And so we can use that information and begin to estimate this area using the knowledge we already have. So we know that we cannot use a specific formula which implies we estimate area using geometry. So when I give you the word estimate, it gives you a little more freedom to go a little up or down the actual area, isn't it? And because of that freedom, we can actually think different ways of using geometry. So what is, and again, remember when I say geometry, we are trying to keep it as simple as possible. So don't look at complicated shapes. Look at simpler shapes. So which shape do you think would accommodate this area as a good estimate? Could we use a square? Could one square kind of hold this area within it? Yes, you can find a square that holds the area within it, but you'll be grossly overestimating the area, right? So if I took something like this, that square would definitely be an overestimate because you'll be almost getting double the area that you're interested in. So that's not going to work. Is there a way I could do it differently? Well, one of the ways that should come to your mind immediately is, can I chop up this area into known shapes? Okay? Because one full shape does not give an estimate for this. So can I chop the area? So how do I chop this? Can I chop it like this? Then what about this one? So we have 3 different areas that I can chop this into, but if you add all these areas, you come back to the square. So we already decided that square wasn't a good idea. So how do I chop this up? So there are various ways we can chop this. So to kind of illustrate this and to take it slowly, let's try to construct maybe rectangles, okay? Because squares are pretty definite. Rectangles will help us to increase the length and increase the width because you have 2 different dimensions that you can adjust, as opposed to a square which has only 1 dimension, meaning all sides should be the same. So you really have not much room to adjust the shape. So because when I say rectangle, I can put my rectangle like this, or I can put my rectangle like this, isn't it? I can do it vertically or horizontally. So here we want to see a way to divide this. So what if I drew a rectangle like this, maybe halfway through, and another rectangle halfway through? That way, it looks as if, oops, I'm sorry, I got the other rectangle. And the other rectangle where it hits the graph, let me take this little more. The reason we do these rectangles is, if I continue the next rectangle right from here, it's the same as getting that big square. So this reduces extra area that you would end up getting when you estimate it, because even here you have this extra area, right? This is overestimation. Yes, there is that danger. There is that overestimation danger. So when I chop this into 2 rectangles, right, it still is not a good estimate because I am gathering a lot of unwanted area. So what's the next step? What do you think we could do to minimize this overestimated area? Well, the natural progression would be to break this into not 2 rectangles but 4 rectangles, and let's see if that is a little better. I know my rectangles aren't great. I'm going to show you a better picture. But do you see that when you divided it into 4 rectangles, the area that we were overestimating minimized? Okay. At least what you're seeing is these first 3 rectangles kind of came out of control. The 4th rectangle is still kind of large. It's overestimated. So what do you think we could go next? Well, maybe divide it into 8 rectangles. And you begin to see that you're minimizing that error significantly. So that's what we're going to see in the upcoming images. Now, what if you thought of breaking this up, like this? what am I trying to do here? Here, I'm trying to divide this in such a way that I'm staying under the curve, right? So I'm staying under the curve, which means I am underestimating, because you see this region will not be counted, because what I'm trying to do is take the area for each rectangle and add them up, right? That's the focus. That's how I'm using geometry here. But in the process, in fact, this whole thing will also go, because if I were to build it under the curve, okay, if I were to build it here, then I won't be able to complete the fourth rectangle. So the fourth rectangle has to end at 1, and therefore this becomes a huge underestimate. So which means I can correct this by maybe going for for 8 rectangles and so on. So what I'm trying to illustrate here is that when you build these rectangles, it's very likely that you end up building the rectangle either outside, so it's overestimation outside the curve, so you bring in more area than what is actually there, or if you want to stay under the curve, then you have the issue of going too low and ending up underestimating. So we call this the upper estimate or the lower estimate. Clear this up and show you this. So here is an example of how we do the upper estimate. When I say upper estimate, we are building the rectangles outside the curve. So you can see the pink shaded region indicates the overestimated area. In this upper estimate, we divided this into two rectangles. We partitioned the entire area into 2 rectangles. And the way we construct these rectangles is, you can actually see that we were kind of looking at the left end point, right? Where the curve meets the end of the circle, end of the rectangle. So the curve meets here, and then you build the rectangle. And then on the rectangle where the curve crosses, you start the next rectangle. This also is an upper estimate, but this is where we have 4 rectangles. The big deal of using the curve where it coincides on the rectangle to build the next one is so that you can get the coordinates, right? You need the coordinates because after all, this is the length and this is the width. That's what you need to get the area of a rectangle, length times width. And in order to get the length and the width, the easiest way to get that information is to get the coordinates. Okay, so for the first rectangle, you can see that the width is 0.5 because that is how far away it is from 0, isn't it? And for the height, or in other words, the length, we have 1 because that's how tall the rectangle is. So 1 times 0.5 is 0.5. That's the area of the first rectangle. The area of the second rectangle, again, the width is still the same. It's 0.5 because you just do 1 minus 0.5 to know what this distance is. But the height of the rectangle, the height, is where the point hits the graph. So what you have to do is plug in this 0.5. 0.5 is half, isn't it? Plug in 0.5 in your function so that you get the corresponding coordinate there to know the height of the graph. The curve gives you the height of the graph, and therefore we are using that information. Okay. If I add these two areas, area of this rectangle and area of this rectangle, I will get a resulting answer that will overestimate the true value. Right? And same is true here when I add these 4 rectangles. What happens is we have the length times the width. Right? In each case, the width is 0.25. We're just dividing it in equal spaces just for convenience because it's easy for us to maintain the same width. Right? What we notice is that this reduces definitely the pink region, right? The pink region is the overestimated region. It reduces it, but we still see that existing. It didn't really completely eliminate it, minimize it. So we're beginning to understand that if I gave more rectangles, it becomes a better estimate because I'm reducing the extra unwanted region. What we see in this third image is that I was suggesting that we divide these 4 rectangles instead into 8 rectangles, right? Half them. So get half of them. Of course, that's not how it'll be. It'll change, but you know what I mean. It'll change because I have to stop here and the next one starts here and so on. But here, this third image actually has 16 rectangles. And you can see how quickly, it's the same region, by the way, 0 to 1, right? 0 to 1 in the end. It's the same region. We're just dividing it into so many rectangles that you do have, especially in the early stages, you see very little extra area outside. Okay? And so that's what we've been illustrating. Now all this is for upper sum. Okay, so I'll just say upper estimate 16 rectangles. So there's only one thing I'm trying to drive home here. The more the rectangles, the better the estimate. Okay, very intuitive. Also, when I say upper estimate, the second message I want to share with you is, when I say upper estimate, I'm asking you to add the areas of these rectangles as a way to estimate the region R that we're asked to find. This is the region R that we're supposed to find. And in order to find that, we are using this idea of approximation, where we add the area of each rectangle. And for that, we are using these coordinates to help us come up with the heights. The height of each rectangle is indicated by the y coordinate at each point, and we can figure out these. So you're dividing this through 16 equal intervals. So there's 1 over 16, 2 over 16, 3 over 16, so on. So you do have x value to input in the equation, get the corresponding y value, and those y coordinates will form the heights of each rectangle. The same can be said for the lower estimate. And here was the case with 4 rectangles. And the lower estimate gets better with 16 rectangles. I would like for us to go back to the upper estimate and learn how to quickly calculate the area, and that way we can look at other examples and begin to work on them easily. So we have two rectangles here. Let's find the area. Okay. So the length would be this, and the width would be this. Sometimes we just call them base and the height. The length would be called as the height, and the base would be called as the width would be called as the base. So it's either length times width or base times height. Okay, any one or the other is the notation we use. That's how we find the area of one rectangle. So the first rectangle we have, I'll just say rectangle 1 plus rectangle 2. So area of rectangle 1 would be 1 is the height. You know the height by looking at this. Also, you know that it's coming from your y coordinate, because that's basically giving you a numerical measure of the height of your rectangle. That's how tall your rectangle is. So 1 times the width is 0.5, right? 0.5 minus 0. I like to put it as a fraction, so I put it as half instead, plus the height of the second rectangle, or the length we say, is 3 over 4. 3 over 4 times the width is still the same, it's a half. 1 minus 0.5 is 0.5, which is a half. I'd like to give the answer in fractions here, so I put it like that. So you want to calculate this. That comes out to be 7 over 8, or if you wanted to keep it in decimals, 0.875. So I should actually say the area under the curve is approximately this, because this is an estimate. Coming over here, this will be area of rectangle 1 plus area of rectangle 2 plus area of rectangle 3 plus area of rectangle 4. And so I'm going to bring in the approximation symbol to make it a little more valid. So A is approximately, again, go by the y coordinate for your height and the distance for your width. So here I just want to illustrate the width by doing 0.25 minus 0. For variety, you can see that clearly, but variety I'm going to keep it here as decimals instead of fractions. And you can very well use your calculator for this. That's area of rectangle 1 plus area of rectangle 2 is this y coordinate 15 over 16 times this distance, which is 0.5 minus 0.2, 0.25, plus area of the third rectangle. These ones are disappearing. That was 1 times. Okay. Plus 3 over 4 times 0.75 minus 0.5. You notice that each time we're talking about a width of 0.25. And then lastly, it's 7 over 16 times 1 minus 0.75. Yeah. So again, if you computed this as a fraction, the answer comes out to be 25 over 32, or if you were to write it in decimals, it comes out as 0.78125. Notice how the area has reduced, because we know for sure we were overestimating, and so the when you went for 4 rectangles, the area reduced, indicating that you were getting more accurate, closer to the true value. And you can very well see that if we went like this for the 16 rectangles, that area will be much smaller compared to the first 2, just because you have better accuracy with more rectangles. While it's good news that your estimate gets better with more rectangles, we certainly see that when we do the upper estimate, you will end up getting more than the actual value, no matter what or how many rectangles you brought in, because you can only have finite number of rectangles for you to add them up. And no matter how many rectangles you had in the lower estimate, you're still going to get an area that is smaller than the actual value. So one is going to give you larger, one is going to give you smaller. Is there a balance in between them? So some of you might be thinking, why not draw these rectangles through the midpoint? Okay. So that is a possibility. Let's see how that looks. Now, if you look at this setup, the first rectangle does not start at the leftmost end of your graph, the blue graph, right? Nor does it start under the curve. Well, the first rectangle's midpoint lies on the blue curve. Okay, that is how you're going to construct it. So what is the way I can draw or construct these rectangles so that the midpoint of that rectangle passes through the or coincides with the blue graph? Well, you get something like this, wherein you begin to see some kind of a compromise. It's not still going to give you the exact answer that we're looking for. It's not going to give you the exact region, the area. But what we see here is, if I had an overestimate, it somewhat balances with, I'm sorry, that was the lower, because it was under the curve. The lower estimate here balances the upper. Likewise, for the second rectangle, this is the lower. So you are not accounting for area here, for which you're balancing off with the upper, which you should not account for. So you see that balance there, and it's making it a better approach, right? So I will just say midpoint rule. So one was the upper, one was the lower. Sometimes we also call it the left and the right. Okay, so the upper and the lower and the midpoint rule are 3 ways to do this. But midpoint rule roughly balances the overestimated regions with the underestimated regions. Now let's look at some problems where we'll try to find all of these things. First, let's start with the upper and lower, and then we will also look at some problems that involve the midpoint. The problem reads, estimate the area using finite sum under the graph of f of x equals x cubed between x equals 0 and x equals 1 using A, lowest sum with 2 rectangles of equal width, B lowest sum with 4 rectangles, C upper sum with 2, and D upper sum with 4 rectangles. Okay. So we need to first draw the graph, then construct the rectangle, and then find the area for each of these parts. To give you a rough sketch, okay, this is a sketch. I'm going to draw this nicely later, but the rough sketch is that you do have y equals, or f of x equals x cubed to look like this, okay? And then they said it's between x equals 0 and x equals 1. So this is x equals 0 and this is x equals 1. So then we are looking at the region that is in between them. So this is basically the region. So you can kind of say it goes from 0 to 1, isn't it? And then it's for this region that we have to construct. So I'm going to give you a zoomed version of this region. So here you see the zoomed version. I have not constructed the rectangles yet because I'm afraid you'll get too cluttered. So what I did was I just marked these positions here, okay? And what happens is, if I were to do the upper estimate, because that was the one of the questions, and then I would go above the curve to construct my rectangles, right? So I'll just show that to you here. So I'm going above, but making sure each time that I touch that, right? So that will be the upper sum. If I were to do the lower sum, I have to stay under the curve. So you can see how then I have to change the rectangles for the other problem. And so for those reasons, I like to keep a visual of the end points and then bear in mind how the rectangles will be constructed. Okay? Let's start with A, which is to find the lower sum. Lower sum 2 rectangles. This is what we have to do. So for that, I have to only look at 0 to half and half to 1. So for my convenience, I'm going to sketch a quick rough one. And that's 1. So if I were to construct a lower sum, I have to stay under the curve. And this would be the first rectangle, which is basically no height. Okay. The second rectangle would be this. Would you know this? So that means the first rectangle has a height of 0. The second rectangle will have a height of half, comma, half the whole cubed, because that's the y coordinate, right? And so keeping that in mind, I would have to write my rectangle. Because they wanted equal width, I'll say divide the interval. The interval that this spans is 0 to 1 into, so divide this into 2 equal parts. So then we get 0 to half, it's a bracket, and then half to 1. You could use decimals too, no problem, but I just like to keep it this way. Therefore, when you estimate the area, it makes it a whole lot easy for us to understand that the rectangle here has length, the length of the height is 0 times the width is half, plus the height for the second rectangle is half cubed, it's always the y coordinate, right, times the width. Let's just write that down here. This is I'll just say height and base. Will that be helpful? So height is the height of the rectangle, and base is of course where the rectangle sits flat on the ground. on the x-axis in this case. Alright, now compute this. So area comes out to be approximately 1 over 2 power 4, so it's 1 over 16. That's the answer for the first part. And we know how to divide it into two equal parts, isn't it? Because basically, this was very intuitive, so you know half of this interval was at half itself. But basically what we do is we take the difference of the endpoints and divide it by 2. That's how we get the half as the point where you should break it. Now let's do the upper sum. Is it the upper sum? No, still in the lower sum. Yeah, lower sum 4 rectangles. So if it is again even or equal width, say divide 0 to 1 to 4 equal parts. So for this, we take the difference of the endpoints divided by 4 because you want it into 4 parts. So if it is 1 over 4, you know that you go from 0 to 1 over 4, 1 over 4 to half, that's the next one. Then it's half to 3 over 4, 3/4. 3 over 4 to 1. Let's draw a rough sketch. So 1/4, half, 3 over 4. Let's stretch this. So I'll just fix this right here. Okay. So now once again we're going down under the curve. So this will be here. This will be the next rectangle. And the last one is here. You do have your coordinates. And what you notice is the heights of these rectangles happen at the left end point of your rectangle, right? That's the left end point. So we can kind of see a connection here and say lower estimate implies left end point, because the left end point is what you're going to plug in to get the height of the graph in each case. So here it's a 0, and so for the area I want to kind of correspond it up here to these boxes. So area is approximately 0 times the width, which is 1 over 4, plus the height, is 1 over 4, sorry, 1 over 4 the whole cubed, times 1 over 4. This point will be 1 over 4, 1 over 4 the whole cubed, plus 1 over half, that's the third end point, times the width is the same, 1 over 4, plus fourth one would be 3 over 4 the whole cubed times 1 over 4. So go ahead and compute all these things. The area comes out to be approximately 9 over 64. So keeping this in mind, I would like to, for part C and D, you can definitely do it the same way as we've done parts A and B, but I just wanted to kind of compile the details we have. Okay, for C, we want to do the upper sum for 2 rectangles, and because we've seen it already, this will will be a half point, this is 1. So your rectangle would be here, and that will be the next rectangle, right? So in other words, you're looking at the right end points. Okay? So I'll say right end points, 0 to half, and half to 1. So the right end points would be half comma half cubed. That's the coordinate there, right, for that one. And for this one, the coordinate is the right end of your rectangle, the right hand corner, and that will be 1 comma 1 cubed. And we know that they are of equal width, and the equal width is the interval 1 minus 0 divided by 2, because you're dividing into 2 rectangles, which is half. Keeping this in mind, the area would be 1 over 2 the whole cubed, which is the height of the y coordinate of the first rectangle, times the equal width half, plus 1 cubed times half. Notice how easy this is, because we've got the idea of how that will behave, right? And so that gives us 9 over 16. And to answer part D, this time we want the upper sum with 4 rectangles. Because it's the upper sum, once again it's the right end point. We have 4 rectangles, so let's remember. Some more, and then we have 3 over 4 to 1. Because these are right end points, again, just do it a little lower here. 1 over 4, 1 over 2, 3 over 4, 1. So this would be the first rectangle, this would be the second one, just to make them. Make sure you have all the right end points marked. So keeping that in mind, this would be 1 over 4, 1 over 4 cubed, 1 over 2, 1 over 2 cubed, 3 over 4, 3 over 4 cubed. Those are the coordinates, by the way. And this would be 1 comma 1 cubed. And again, equal width, 1 minus 0 over 4. That's how we even got to divide this interval. Alright, so the area would be, take the y coordinate of the first interval, 1 over 4 the whole cubed, times the equal width, which is 1 over 4, plus 1 over 2 the whole cubed times 1 over 4, plus 3 over 4 whole cubed times 1 over 4, and lastly 1 the whole cubed times 1 over 4. Take a little bit of time to compute this. Take the time, pause the video, and then you'll see that actually it comes out to be 100 over 256, and reduce that, and that will give you 25 over 64. What you notice is, as we keep doing these problems, we begin to evolve better ideas or better techniques. Like in this case, we found that if we were to construct the rectangles from for the lower estimate, we use the left end point. For the upper estimate, we use the right end point. It's also intuitive, right? Left, lower, right, upper. So we'll do the same problem now, but I'll give you a different function. We should move faster first. So this time our equation is f of x equals 1 over x between x equals 1 and x equals 5. This is very interesting. So you know your if you were to sketch this, you have these two branches, so 1 and 5. So we are interested in this region between 1 and 5. Just use this to shade it. That's the region we're interested in, and that's the region we need to divide into two rectangles, 4 rectangles, lower sum and upper sum. So the best way for me to kind of compile all these things is to use the technique we figured out towards the end, where you can first talk about equal width. Let's measure the equal width. So we know that it's the interval is between from 1 to 5, right? So take the difference of the intervals. You divide it by 2, which gives us 2, 4 over 2, 2 for 2 rectangles. That's shortcut for rectangles. And it's going to be 5 minus 1, the difference of the interval, over 4, which is 4 over 4, 1, for 4 rectangles. So before I do A, B, C, D, I compile my details here so it's easy for quick reference. Then what we do is the left end points will be considered for lower sum, L and L, lower sum. So for that, when we have 2 rectangles, okay, the left end point, so you're going to divide this interval into 2. So you're going to go from 1 to, so add 2 to this 1, okay, 1 to, because this is the 2, that's the equal width. So 1 to 2, 1 plus 2 will give you 3, then from 3 you move to 5. So the 2 intervals will be 1 to 3 and 3 to 5. Do you notice that? That will give you the left end point, right? So that's left end point is 1, 1 comma 1 over 1, and this left end point is 3, 3 comma 1 over 3. 1 over x is the function, so do 1 over 3. And then I'll do the right end point. This is for the upper sum. Two rectangles. Same thing, 1 to 3. Right? The interval will be broken the same way, but you're using the right end point. Right end point is 3. That's going to be 3 comma 1 over 3, and the right end point there will be 5, 5 comma 1 over 5. So here again I want to point to this. It was the left hand point, and here it was the right hand point to help you build your coordinates. And when you build the coordinates, you're focusing on the y coordinate to get the height of your rectangle. And then I want to do the left end points for 4 rectangles. You could have done this right under the 2 rectangles, that's fine. I just wanted to keep the intervals cozy there. Here I'll have to go 1 to 2 because I just have to do 1. Right? I need to divide this 1 to 5, this region, into 4 equal parts, and the equal width is 1, so 1 plus 1 will give me the second marking, which is 2. In this case, 2 plus 1 is 3, and so on. Previously for just 2 rectangles, I just had to add a 2 to this 1. That gave me 3 as the middle value for 1 to 5 interval. Okay, so it's 1 to 2, 2 to 3, 3 to 4, and 4 to 5. And so the left end point, 1 comma 1 over 1, 2 comma 1 over 2, 3 comma 1 over 3, 4 comma 1 over 4. And the right end points for 4 rectangles. If you want, you can write the interval again. I'm not going to do it. So I'm choosing the right that's going to be 2 1 over 2, 3 over 3, 4 over 5. Alright, that's our setup. Now we can go right into A, B, C, and D. A was lower 2 rectangles. That means my area, we go back, quickly reference it. So the width is, again the equal width was 2, so nobody's there, it's always a 2. 2 times 1 over 1 plus 2 times 1 over 3. Okay, that's the width. We were calling it the base, right? And this is the height. Okay, you can do base times height or height times base, doesn't matter because multiplication is commutative. So that will give us 8 over 3. We go with B. B was lower with 4 rectangles. So area was, the width was 1, right? So 1 times 1 over 1 is 1 times 1 over 2, 1 times 1 over 3 is 1 times 1 over 3. Notice that if you come back here, the left hand points were 1 over 1, 2, 3, and 4. So that's what we're multiplying with the width. That comes out to be 77 over 16. C was upper with 2 rectangles. And 2 is, the width is 2, you know that. And that's going to be 1 over 3 and 1 over 5. Let me quickly take you back there. I should show that to you. The right end point, right? Upper is right end point, so the y coordinate is 1 over 3 and 1 over 5. And the width was 2. Okay. And then we have that approximates to 16 over 15. And then we have the upper sum for 4 rectangles. So 1 times 1 over 2 is 1 times 1 over 3. 1 over 5. And that comes out as 25 over 12. Okay, so I kind of showed you 2 ways of doing it. One is the traditional way we construct these rectangles visually and then find their area by taking the length and the width. And then in the second example, I gave you a visual of this without really having to look at the rectangle, but just understanding that lower sums will include the left end points and the upper sums will include the upper end points, and you can basically do this even without looking at the graph itself. The next concept here is average value of a non-negative continuous function. Let's just focus on the word average. Average value, right, would mean that you took the sum of all the items and divided by the total number of items. That's your average. So you add them all and divide by the total number. So if you had n items, then you add all the n items and divide by n. Then when we talk about a continuous function over an interval, say a to b, how do you find the average value? Because because of the continuous nature of the function, it has so many different values, infinitely many values that this function has. So we cannot really think about doing it as we would do the average, where you add the numbers and divide by n. So in other words, like when they say the temperature, okay, of say Merced in any given day is a continuous function, because the temperature goes up and down. It's not one same value throughout the day, isn't it? And in fact, every moment it goes up or down. We may not detect it, significantly, but it goes up and down constantly, changes. So what does it mean when they say the average temperature at Merced over the course of the day is 80 degrees. How did they come up with that number if it's going to go up and down continuously every day? So you see that understanding the average value of a continuous function is very, very practical. We use this in every day. Well, what we understand is if the function is constant, right, if it is not going up or down, it's steady, it's a horizontal line, then we have no problem because the average value will be that very point where the horizontal line passes. But if it goes up and down, what do we do? So think of it like this, okay? Say you have a tank, okay, filled with water, and this water is sloshing around in the tank, okay? It's sloshing around, and the tank is enclosed between the two walls, like in our case, x equals 0 and say x equals 1. Instead of that, we now have a to b, so x equals a and x equals b. These are the two walls of the tank where the water is sloshing. Now, if I want to find the average height of this water, I can't do that because it keeps changing because it's sloshing. So what do? In order to find the average height, I have to wait for the water to settle in the tank, and when it settles, then I know that once it reaches a level, we know that that's the height and that's going to be constant, and so that gives us the average height when you're able to measure it when it's settled. So that's the whole idea that we're going to use here in this finding the average value of a non-negative continuous function. So as I mentioned, now in this figure, you can think of water sloshing. Okay. So you can't find the average height. So you'll have to wait for the water to settle here. Settles and is level, you can say. And because it's level, you know that that's the same height that you will have as the average height when the water is moving. Okay. So keeping this idea of knowing that the average height is there, but when it's moving around we can't see it visibly, we can use the idea of area to answer this question. So what do we do there? We take the area, okay, area is, we just saw roughly, it is the length times the width. Yeah. And we also saw that in different language. We saw that as the height times the width. The base. This is again approximate, right? Because we've been approximating it all along. So what we need to do is find the height. And in order to find the height, just rearrange the variables. So you'll get height is nothing but area over base. Okay. So I'll say average height is nothing but the area under the graph or under the curve, graph curve, so to say, over the base is the width actually of the interval b and a to b. A to b is the interval, so the width will be b minus a. And so that is how we find average height when you have non-negative continuous function where the function goes up and down, it's changing continuously. It's not constant like this where you could have found the value right away, but when it's moving up and down constantly, we use the idea of area to find that value c where it is constant. So in other words, that's the average height or the average value. Estimate the average value of the function f of x equals sine x on the interval 0 to pi. 0 to pi. So let's again draw a rough sketch of, we're only using the positive side, so I'm just going to only focus on the positive side of the graph. You know, your sine function looks like this, right? For one period, this is 0 to 2 pi. That means this is 0 to pi. And the focus is on just this region. What is the average value? They didn't ask us to find the area under the curve, they want us to find the average value. So this is what we want, and that means I'll have to build rectangles. I can use well, before we build rectangles, if you recall, we said the average value is area over the difference in the width, I'll just say. In this case, it's pi minus 0. So it's area over width, and area means that we have to do finite sum approximation. That's the language for it, meaning constructing rectangles. For that, we could do lower, upper, or midpoint, one of these three. But remember, in any of these methods, it was successful in the sense it became as very close to the true value only when we kept our rectangles very thin, meaning if we had more and more rectangles, the estimate got better. So no matter what method you use, make sure that that's considered, okay, as many rectangles as possible. And then to find the width, that is b minus a, which is in this case pi minus 0, which is pi. So we got the width already, we need to find the area. And then if we take the area over the width, that will give us the average value. Okay? So our width is pi. To keep it manageable, maybe we could divide this into eight rectangles. So it will look like this. Okay? 8 rectangles. Now I'd like you to again remember that the heights, because I'm using and I'm also going to choose to do the upper sum. Okay. So I'll just come back and write all that information here. So upper sum, 8 rectangles. So we know upper sum means we have to use the right end point, and if it's 8 rectangles, then we are dividing this region, pi minus 0, these ends, into 8 parts. So it's going to be pi over 8. So that will be the width of each rectangle. Alright, I think we've got all the details we need. So we have, again for quick access, I'd like to enter these values as pi over 8. This point will be pi over 8, right? 2 pi over 8. I don't want to reduce it because it's just easy for me to keep that count going. 3 pi over 8. This is 4 pi over 8, right? Pi over 2 is 4 pi over 8. This is 5 pi over 8, 6 pi over 8, 7 pi over 8, and pi will be the same as 8 pi over 8. That's how you know you kind of accounted for it correctly. Alright, so if you looked at this end point here, we're looking at the right end point. So for each rectangle, you're looking at the right end point. That will be pi over 8, comma, sine pi over 8. If I were to write for each one of them, it's going to get pretty cluttered. So keeping the visual here, I would like to write the area. And the width is pi over 8, so I'm going to put the width first. So width times the height of the rectangle is sine pi over 8 plus times sine 2 pi over 8 plus sine 7 pi over 8. Would you do, because you're in a flow now, would you do plus pi over 8 sine 8 pi over 8? No, bear in mind that you're only looking at the right end of each rectangle. So you have the right end kind of ending here. This right end does not coincide with for the last rectangle, it does not coincide with your with your blue curve, so you cannot use the last rectangle. Okay, so and the two rectangles share that endpoint right there. So, well, you also have to account for all the rectangles, so we do have that. Now it's definitely a lot easier to use the decimals using your calculator with the decimals. In fact, you can factor out the pi over 8. You must have seen this already. Pi over 8 times sine pi over 8 plus sine pi over 2 pi over 8 plus sine 7 pi over 8. Now this is easier because you don't have to multiply by pi over 8 each time. So that gives us pi over 8 times 6.02. Use the pi key in your calculator, and that gives you 364. Now all this is to find the area. Okay, this is the area now, or estimate of the area. Now we need to find the average height, which is area over width. So the area is 2.364. I should say approximately, right? This is the average area. The average area, therefore, comes out approximately as this over pi. And that comes out to be approximately 0.753. Now, remember, we are kind of building the idea of how to estimate the area, but we do have a way to find the exact area. That's what calculus helps us to do, right? If it's just estimation, why would we need calculus? We just got that done through geometry. So we are going to go towards that. So keeping that idea in mind, where we will find the exact value, we see that if we did, or just say for exact area, okay, the exact area using calculus, what we find is the average height is area, which is 2, not 2.364. Okay. Remember, again, it has to be lower than this because we overestimated it, right? It was the upper sum, so we overestimated it. So the value, actually, the true value, the true area is 2 over pi, and that approximately is 0.63662. We are kind of off, but not terribly off, and so we were able to estimate this. And again, because I used only 8 rectangles, okay? Even if you use 16 rectangles, we would have gotten much closer to the true answer, which is 2. And so just for practical purposes, I kept it at 8. That still gave us a decent approximation. So I hope this was helpful to you. And this is how you will calculate the average value of functions, where you find the area like we did before, and you can choose any approximation style, lower, upper, or midpoint. And remember, for average height, you have to divide by the width. But when they just say find the area using finite sum approximation, then you just find the area and stop right there. All right. So I hope you enjoyed this video. I will see you in the next one.